We're group number 1, and this is our levitator project. So the primary goal of our project was to design and construct a magnetic levitation system that was capable of suspending objects using the force of a magnet. Through this project, we aim to explore the principles of electromagnetism and feedback control systems while showcasing practical applications of these concepts we learned in class. The components used in this project was a 12-volt magnet, an Arduino Uno microcontroller, an AC to DC converter as a main power source, a Hall sensor, a voltage control circuit for regulating the magnet strength, a LED indicator so we could easily monitor the Hall sensor's response to the magnetic force, and then we used a 10 centimeter mounting setup for suspending the magnet and conducting our testing. So the main component of our project was a UXL 12-volt DC 250 electric lifting magnet. We got this from Amazon, and the magnetic unit can generate up to 4 amps when it was fully powered. So for our magnet,
to be able to have full control of the corrective action, we used a hardware approach. For our driver circuit, we wanted to be able to control the strength of our magnet's fields at any moment. We used a circuit that utilizes a MOSFET and a potentiometer as the main components for control of the feedback loop. This type of circuit is a MOSFET and potentiometer driver circuit, and its main purpose is to regulate current and voltage. The circuit configuration utilizes a IRF Z44N MOSFET, which is an electrical component that is known for its features like low resistance and high current handling capacity. Along with the MOSFET, we decided to use a 50 kilo ohm variable potentiometer to allow us to have full control of our driver circuit. The addition of the potentiometer allows us to create a versatile driver system for precise regulation of both current and voltage, crucial for controlling the magnetic force generated by the magnetic device. The MOSFET has an N-channel design which serves as the primary switching component that ensures power management. The potentiometer is connected between the gate and source terminals of the MOSFET. Manipulating the potentiometer, we can fine-tune the VGS, thereby modulating the current passing through the magnet, which ends up with a change in the magnetic field. This circuit can directly control the intensity of the magnetic field generated by the magnetic device. Throughout the project, one of our primary challenges revolved around selecting the most optimal sensor for our magnetic levitation system. Initially, we experimented with an ultrasonic sensor, only to realize that its gain and range were far too excessive for our application. Recognizing the need for a more suitable alternative, we then attempted to implement an IR sensor, but encountered the same accuracy and range issues. Ultimately, we found our solution in the form of a Hall sensor. This choice proved to be the most effective as it seamlessly integrated with the code for our PD controller and consistently provided accurate outputs. The Hall sensor compatibility and precision were instrumental in ensuring the smooth operation of our magnetic levitation system.
An additional feature we incorporated into our hardware setup was an LED indicator system. This LED system provided a convenient visual cue, enabling us to discern where a sensor was actively detecting magnetic fields and when it wasn't. This addition proved invaluable during our testing phases, allowing us to easily determine whether our system was sensing magnetic strength or not, especially when objects were present. Here's how it worked. When the green LED illuminated, it signaled that the Hall sensor was out. For our microcontroller, we opted for the Arduino IDE. This choice was ideal for us because it enabled us to program the PD controller using C++.
Begin by defining some constants and variables. We specify the pin for the Hall sensor as well as pins for 2 LEDs, one indicating a positive control signal and the other for indicating a negative control signal. The proportional gain Kp dictates the magnitude of the system's response to the present error. A higher value of Kp amplifies the corrective action in proportion to the current error by enhancing the system's responsiveness. A lower value of Kp would give a more subdued response by potentially reducing overshoot and oscillations, but reducing speed of correction. In addition to the proportional gain, the derivative gain, Kd, governs the system's response to changes in air over time. By considering the rate of change of the air, Kd enables the PD controller to anticipate further trends by adjusting the control signal, enhancing stability, and damping oscillations. However, excessively high values of Kd introduce noise amplification and instability. Within the setup function, we establish serial communication for debugging purposes and configure the LED pins as outputs to facilitate visual feedback. Moving on to the loop function, we continuously read the analog value from the Hall sensor, convert it to Gauss, and then to Tesla. We compute the error, which is the difference between the desired magnetic field strength and the actual value measured by the Hall sensor. Next, we calculate the control signal using a proportional derivative controller. The control signal is adjusted based on the error and its derivative, with proportional and derivative gains, Kp and Kd respectively. We also incorporate an integral term to handle steady-state errors. Finally, we use LEDs to indicate the direction of the magnetic force. One LED lights up when the control signal is positive, and the other lights up when the control signal is negative.